Okay, so let's continue the lectures about functional linear regression models. On Monday, we talked about there are three types of functional linear regression models. So this Monday, we talked about the response is a scalar variable and the covariance is a function. So we call it scalar on function regression models. And there's also two other cases. The first case is when the response is the functions and the covariance are scalar variables. So these scalar variables can be group labels, like some discrete variables, or can be a continuous scalar variables. So today we will focus on these two cases, and there's another more complicated functional linear models when both response and covariance are functions. So we will talk about this the third models later on. So let's first focus on the first two cases when the response is a function and the covariance are scalar variables. So when the covariates are discrete or the some group, we also call this functional linear regression models as functional ANOVA. This is exactly the same as so for in the linear regression case, we have when the covariates are group, we also have the ANOVA models, right? So this is kind of a functional version of ANOVA models. Okay, so here is give you the ideas, one examples for this functional ANOVA. So again, we are focused on the Canadian temperature data. So these figures we have showed before. This is show the daily average temperatures in 35 Canadian cities. So we know Canada is a large country and we have very different weather. So we roughly can split Canada to four regions. One is the region on the very east of Canada, close to Atlantic. One is we call it continental, like in Ontario, Toronto, Montreal. So the third area is like the city is close to Pacific, like Vancouver, Victoria. There's another regions is on the north of Canada. We call the Arctic. So here, one question we want to address is that we want to know whether there's any difference among these four regions. So this is the question we want to ask. So here, in these figures, it also color the temperature for different regions with four different colors, and you can see, like for example, the Arctic regions has apparently low temperature overall, right? So for the blue curve, which is the continental area like Toronto, Montreal, you can see their temperature in the summer actually is pretty close to the Atlantic and Pacific regions. But in the winter, it can drop down very, can be very cold, right? So can be minus 20 or something. So for the Atlantic and the Pacific, their summer are pretty close. But you can see these red curves, which is Atlantic cities, their winter is colder than Pacific. Okay, yeah, so this is kind of what this is some information we can see when we look at this data. I also want to emphasize that for functional data, it is very complicated. So I always encourage you to plot the curve first and make sure you take a look at what the data looks like before you're doing any analysis. This is very important. Okay, so now let's look at how to do this ANOVA, functional ANOVA. So here, this is the notation. Xijt represent the S curve in the J's group. Suppose in group J, there's NJ curves. So first we can calculate the overall mean, right? So we can just average across all the curves. We can get the overall mean curve. And then we can look at the effect of each group by looking at the difference between the average curve in each group minus the overall mean curve, right? So in this expression, basically the first term is the average in each group, average curve in each group, and minus the overall mean. So this is alpha JT represent the effect for the J's group. And then we can calculate the residuals, which is the curve minus the overall mean curve minus the regional effect curve. So this is the simple ANOVA models, right? You just want to look at the group effect on this functional data. So we can put this in more general framework when the covariates are either group or some scalars, continuous variables. So then the model can be written as YIT equal to beta 0t plus summation beta jt times Zij plus epsilon I of t. So if you familiar with the literature, in some literature, this is also called a very coefficient model, right? The reason is because if you look at the beta j as a coefficient to the Zij, this coefficient is changing with time, right? So they also call varying coefficient models in some literature. So for the varying coefficient models, those coefficients can be a function of any covariate. So in our case, these functional models, a special thing about this functional model is that these coefficients is only vary with the time. So it's in certain ways it's not that general as the very coefficient models. Okay, so this is the model we have. We also call this model as a function on scalar linear regression models. So here we assume that the random error epsilon I of t has mean 0. So our objective is to estimate beta 0 of t and beta j of t. So here beta j of t represent the effect of the J's scalar covariates Zij on the functional response Yi of t. Any question about this model? Okay. Yes.
So like back to the weather data.
Yes.
So it's like J, I, J. They are like the regions.
Yes. So Zij will be the regions. So for these weather examples, Zij will be equal to 1, 2, 3, 4, representing these 4 regions.
And it's not. Okay. So for so like J is gonna be from 1 to 4, to the number of regions.
Yes.
Okay. So Zij is not like gonna change with i's. So they're just
Zij can change with I, right? Because if you think about there's 35 cities, I from 1 to 35. So this Zij can be 1, 2, 3, 4 for the 35 cities.
Okay.
Yeah. Yes.
Oh, so I is the.
I the index for the city in our case for the weather examples.
Oh,
J is the index for the region.
okay.
Yes. So now we have these functional linear models, and you can see here we can retain this Zij in a vector form, right? So if we retain this a vector retain this functional model in the vector form, so if we define a new covariance vector, Zi equal to the first element equal to 1, the rest is Zi1 to Zip, then this can be written in this vector form, right? So this is exactly like the multiple linear regression models. And for any given time, this is exactly the multiple linear regression models, right? So then we can estimate this for any given time. We can estimate beta of t as this using the least squares estimation, and we can get these estimators. Okay, so this is the result we got. The problem when we using this method is that we don't have any smooth controls on the coefficient beta of t, right? Basically, you can look at here. Beta of t is just a big matrix multiplied by y of t, right? So beta of t, the roughness of beta of t really depends on the roughness of y of t, right? So we have learned in our previous functional linear regression model that in many cases, actually you want to get a smooth estimate on the coefficients. Firstly, you want to, which is help you to know, to find out the real effect. And also you want to make the estimation result more stable. And also you want to make the estimated beta t help you to interpret the effect, right? So therefore, we don't recommend this this method. We would rather to want to doing some smoothing controls on the coefficient function beta j of t. So to estimate a smooth functional coefficient beta j of t, this is the thing, and we have learned in our functional data. We will first represent this functional coefficient beta j of t as a linear combination of basis functions. So we write beta jt equal to phi j of t. This one will have a transpose times cj. So cj is the basis coefficients, the vector of basis coefficients, and phi j of t is a vector of basis functions. So then we can estimate this beta, the basic coefficient Cj, by minimize the sum of square errors. So in our case, because we have the functions, so we will just take the integral of yi of t minus zi times beta of t square. Okay. So if we have y of t and beta of t share the same basis, or we don't have any smooth control on the beta of t, this will be exactly the same as the pointwise solution. And so now we will try to add some roughness penalty on the beta of t to make a beta of t smoother. So before we add in the roughness penalty, I also want to show you some the algebra to estimate the basis coefficients. So suppose we can represent this beta of t as a linear combination of the basis functions, like beta t equal to beta j of t equal to phi j of t times cj. Then basically, because the basis functions are selected by us, so we know this is phi j of t. So we can combine phi j of t with zj here, right? And we will just leave cj there. So so we combine this z function, z the scalar covariance with the basis functions. We define this new basis functions phi I of t, which has this scalar covariance information there, and then you can doing the linear algebra, and you can written these sum square errors as a quadratic form of these basis coefficients, and then you can doing the derivative of the sum square error with back to the basis coefficients, and then you can solve for the basis coefficients. You will get this formula. So this is very similar to the least squares estimation, but here we kind of written this in the way that we using the basis functions in the formula. Okay. Any question in terms of this estimation? Okay. So for functional ANOVA, so this is the functional ANOVA models, right? For functional ANOVA, there's actually a one constraint. So for our example, for our weather data, we have 4 regions, right? And each alpha 1 to alpha 4 of t represent the regional effect, which is the region mean departure from the overall mean, right? So, but you can think about there's a constraint that this difference, the region effect, the 4 regional effect, adding together, the summation should be equal to 0 to make it identifiable, right? Yes. So how can we deal with this constraint? Any ideas? How can we add in these constraints in the estimation?
Adding a penalty?
Adding a penalty, yes. We can add in a penalty there. Yes, it's like a Lagrange optimizer, right? Yes, we can do that. There's another way we can do is if you think about, we can written these constraints as the actual equations. For example, we can define another response. We can look at this 0 as a response, right? And then we can retain this summation alpha jt as another covariate. So maybe let me see. So basically, for these constraints, you can retain this as so if you have the put the parameters as a vector form. So mu t, alpha 1 of t, alpha 2 of t, 2, alpha 4 of t. If you have this, so this is the vector of the parameter you want to estimate, right? So in this case, actually, you can retain these constraints as 0, 1, 1, 1, 1, right? So then this will be the exactly looks like the model you are using. But now for this case, you know the response is equal to 0, right? Because for all other xjt, you can retain as the same vector of the parameters. So for all other xjt's, they will be just 1, 1, 0, 0, 0, and 1, 1, 0, 0, 0. So you have all these design matrix, right? Yes, for all other xjt's. And for these constraints, basically you will add another column 0, 1, 1, 1, 1 with the same vector parameters, and you will add this one extra rows of response. Then this will be exactly the same, right? Yeah. So this is kind of a easy way to deal with these constraints. Okay. If we do this, we can estimate this vector of the parameters by using the least squares we just introduced before. Is this part clear? Okay. So this is the result we got for our temperature examples. So yes, I think here this is strange. Yes, I think there should be a shift, kind of sign should multiply by -1, right? So the shape of the temperature should be like a bell shape. Okay, I think this is kind of opposite. I will double check about this part. Okay. So we can test the significance of the covariance by defining the pointwise f static. So the pointwise f statics, it will be equal to the ratio of the variance of the fitted curve. This is kind of the variance of the signal record, and the denominator will be the sum squares of the residuals, and this will be the variance. Can we look at the variance of the noise? So we can look at the ratio between the signal to the noise. This is one way we can do. We can also, so this is kind of doing the pointwise hypothesis testing on the significance of the covariance. Another one, sometimes we want to ask is whether there's an overall effect of the covariance on the response. So one statistic we can use in the maximum of this pointwise ratio f of t. Okay, so but we have no ideas about the distribution on the f star. So what we can do is if you don't know the distribution, what you can do is you can do in the permutation test, right? So how many of you have known permutation test before? Can you raise your hand if you know permutation test? Okay, so permutation test is a very popular test to test the association between covariates and the response. So the ideas is that so this is a test to test the null hypothesis, the beta j t equal to 0 for all j from 1 to p. Okay. So this null hypothesis represents there's no effect of the covariates on the response. So for the permutation test, what we do is that we will fix the. So when we have the data, we have the pairs, right? So the pairs is that we have yi of t, and we have this covariates xij, right? So this is coming with the pairs, and so this is the functional response for the ith subject, and this is the covariates for the ith subject, right? So they have they kind of have a pair together. So when we do the permutation test, what we do is that so suppose we have these pairs, like suppose we have only one covariance. We have one xi1 and y2t xi2. Sorry, x11, x21, and until yn of t and xn1. So we want to test the association between the covariates and the response. So what we can do is we can permute. We can permute the response. Basically, you will randomly rearrange this response, okay, and you will fix this the order of these covariates. You will permute this response. So if you think about if there is no association between the x and the y, then the estimated residuals will kind of look similar, right? Yes, yeah. So we permute this response, and then we will estimate the models, and then we will estimate the residuals, and we will estimate the statistic we use. So we will look at how extreme of this. So after we get this, we can do this for b times, right? Like for 100 times, for example. So for 100 times, we are able to find the histogram of these statistics, right? And then we can look at what's the percentiles of this f star from the original data on this kind of the distribution of these statistics under the null distribution, right? Under the null hypothesis. So you can understand this FB star here represents the distribution of the statistics under the null hypothesis, right? Yes. Okay. So this is the permutation test. You can do this. And so this is the result from our temperature data. And so this solid lines is the observed pointwise F statistic. And this dotted lines is the pointwise 5% critical values from the permutation test, and this horizontal dashed lines is the maximum of this 5% critical value from the permutation test. You can see apparently the F statistics obtained from the real data is much larger than the 5% extreme from the population of the null hypothesis under the null hypothesis. So therefore, we will see that there is a significant regional effect here. Okay, so this is a summary for what we learned. So you can see we looking at the new models when the function is the response is the function. Yes.
Okay. Could you go back to the last slide? So we compute this F statistic for every single day. So we do the permutation test for every single day's worth of stuff.
Yes. Yeah. So basically, when you're doing one permutation, when you permute this response, you are able to get a pointwise
For the one.
F statistics, right? You will get a one type of this curve, right?
Okay.
Yes. Yeah.
So if the F statistic dips for only some points, are we saying that those days,
Okay.
like,
Yeah. So if some of this is under these critical values, what does this mean, right? Yes. Yeah. This is a very very good questions. Yes. So I guess so for example, when you do it's for each permutation test, basically you will get a dotted line like this, right? So you will get 100 dotted lines, for example, when you're doing 100 permutation test. And if in some regions, sometimes this pointwise F statistics is under this population, the critical values for the pointwise F statistics, you can see that there's no regional effect in that time period.
right?
Yeah, something like that. Yes. Okay. Yeah. Okay. So we learned this permutation test to test the effect of the covariates. So any questions so far here? Okay. Yes.
Can you go back to the previous slide?
Yes.
Just like the maximum critical value,
Yeah.
is that simultaneously calculated based on all the points, or it's something else?
So yes. So what this maximum 0.05 critical value means? So it means that for each permutation of the response, you can get these dotted lines, right? So after you got these dotted lines, you can look at the maximum values of these dotted lines. For example, for our case, so this case here is here, right? You get the maximum. Okay. So then you're doing this for 100 times, 100 permutations. Then you will get 100 maximums, right? And then after you get these 100 maximums, then you will order these 100 maximums, and you find the 95 of the maximum. Do you see what I mean? Yeah.
But like this pointwise critical value is based on only one permutation. So
Pointwise pointwise. This is also based on 100 permutation.
it's the mean.
So yeah. So this is like so for each permutation, you can get one of this curve, right? And then you can do 100 times, and you get 100 curves, and then you will find these critical values for each given time points. So basically, you will look at the vertical. For example, in this 100 days, right? In this 100 days, you can get like 100 F statistics here, and then you can look at the 95% percentiles of this critical value, get the critical value. Yes. Yes, Brenda?
Just to clarify, the dashed straight line,
Yes.
you're saying that is a maximum we got in one of those curves that we got, and it's the maximum associated with the 95th percentile curve.
No, it's
Maximum, not the curve, the
maximum.
maximum from the curve.
Yes.
Okay.
Yes.
Okay.
Yeah. Yes. Yeah. So basically, here, you will get so for each permutation test, you will get this maximum, right? So F I'm using F star here. F star B, right? So you will get F star 1. So this is the maximum over the whole year, right?
Right.
Yes. Yes. And then you will get another on the second permutation. You get the maximum over the whole year,
Okay.
and then you will get this 100, and then you will find the 95 percentiles of this maximum. Yes. Yeah. Okay. Is this clear?
Yeah.
Okay. Yes. Okay. Yeah. So this permutation test actually is very, very powerful and handy when you test the association between X and Y. So in genetics, there's a big question to test the effect of the genes on some response we call trait. So in that case, the permutation test is used very often to test the association between the genetics and the traits. Yes. Okay. Maybe let's stop here, and we will continue after 10 minutes break. Okay.